here is they were really hoping that you remembered how you set up the areas of a regular polygon. It's 48, I think, is that right?
45.
45, that's close.
Not really. Not kidding.
Anyway, so the area of a regular polygon is 1/2 the perimeter times the apical. Now, when you break it down, no matter what, with every single regular polygon, you always had 3 sides connected. Remember that? This is where I drew this over and over and over again whenever we did regular polygons, because it's, bless you, because it forces you to know that there's a center, apothem, perpendicular bisector of a side, radius bisects the corner angle, and you have an exterior angle. What's wrong with you?
Because yesterday at the math team thing, I said something about the radius, and Grace was like, "There's no radius in a polygon. That's just for circles."
No, it's when it's inscribed. If you were inscribe a regular polygon, the radius is the from the center where the apothem comes from to the vertex of the regular polygon. The vertices of regular polygons touch the outer edges of the circle.
But so if it's not inscribed, it's just a regular polygon, is there a radius?
In a regular polygon?
Yeah.
Yes. In a regular, no matter what, anytime you have a regular polygon, your regular polygons, the way that they are, or any one of these, from the center to the vertex, is always a radius. It's always the radius because you can inscribe any one of these into a circle, and it hits it right there. That's the reason why that works. Okay? Yeah, you're right about that whole areas thing.
See, maybe you just had to try harder.
Yeah, dude. You just start on my desk, please. If you don't mind. Thank you. So here, I was also hoping that you guys remembered that when you're working with regular polygons, you had interior and you had exterior angles. Which ones were always easier to find?
Exterior.
Exterior, because what was the sum of the exterior every time? 360. Now if you have a hexagon, how many angles does a hexagon have? 6. 360 divided by 6 gets you, which means your interior whole angle is 120, which means the bisected part is 60, which gives you 30, 60, 90 triangle. Now, the problem itself told you that it had side lengths of S. It had side lengths of S. I'm going to change that to X. The reason is my S's look like 5s. My X's, well, they look like X's. So if this is an X, it's bisected here and here, which means these are both X over 2. They're half of it. You okay with that? Now, inside this, with the apothem one side and the angle, we have a 30, 60, 90 triangle, which had you the ratio. Yes, ma'am?
Is that corner a 60 in the triangle?
This corner here is a 60. The exterior is 60, which means the whole angle is 120, and the radius bisects it. Now, it gives you the 30, 60, 90 triangle. 1, 2, root 3. Remember that from Seth? Or from me? Judkins, whomever. X, x root 3, and 2x. You know across from the 30 is some value, well, we'll say this is, we'll write it out this way. Since I drew up my diagram as, in terms of x's and things like that, I'll use y root 3 and 2y. Across from the 30 is some value y. Across from the 60 is y root 3. Across from the 90 is 2 times y. I know across from my 30 is this value of x over 2. So that means across from my 30 is x over 2. Across from my 60 is x root 3 over 2. Across from my 90 is double x over 2, and you get x. So in a hexagon, you might have recalled this from last year, the hexagon, a regular hexagon, the triangles that are formed, the 6 triangles, they're all equilateral with side lengths of x. It asked you then to figure out the area of this lower portion triangle. Bless you. Oops. This is my height. So the area of a triangle is 1/2 base times height. The base of this triangle is x root 2, otherwise known as x. The height is x root 3 over 2. So your final result here is the area of that triangle is 1/2 your base times height, which gives you 1/2 x root 3 over 2. What's x times x? And what's 1/2 times 1/2? 1/4. So you get x squared root 3 over 4 as your overall area. I think it was just giving you the formula, I thought.
I thought it gave you like the whole area.
It did. Oh, that's right. It did give you the whole area, but this is how we get to the formula. I think now you had to find the side length out of it. Thank you, Joseph. And you're right. Somewhere up here it said something.
Was that something like they put it in just to like confuse you?
What do you mean?
Like when they put stuff in the equations that like it's just there, it's like a filler. Like you know when they say like Bonnie has blue shoes and green shoes. And
No, you actually had to know how to set that up. I mean, they gave you, if you look at the diagram isn't all that great. They gave you the height here is s root 3 over 2, and a side length of s. So you could have gotten through all of that, but if you weren't sure where all that was coming from, that's why I worked it out long form.
I couldn't really.
We're getting there. So lastly, if it says 450 is x squared root 3 over 4, well, both. Oh, thank you. Yeah, it's over 6, because you're saying, you did say there were 6. That was the whole trade. Yeah. So it's over 6 because there are 6 of those triangles. The 450 was the entire tray of veggies, the veggie platter, if you will. So the 1/6 of the veggie platter would be 1/6 of 450. So what is that? You said 75? Yeah, 5 over 3. Yeah. So 75 is that x squared root 3 over 4. Multiply by 4, we get 300 x squared root 3. Divide by root 3. Rationalize. We get 300 root 3 over 3, which simplifies out to being 100 root 3. And then you take the square root of that. Just kind of ugly. I think it gets asked for decimal, didn't it? Well, what is the area of the bottom triangle? 75. How can you, the diagram at the right, use the formula for the area of the hexagon? Oh, you didn't even have to find side length. Huh. Read instructions. You know, it's kind of like fractional forms of ratios.
Mr. Seth always tell us you're just gonna put like a direction right at the top that says like don't do anything on this test, and then we don't just do it.
I've done that before. I've done it before. It's crazy. People do. I do it, and people don't even realize it.
You should.
I've told you before. I've had a kid. 6 or 7 years ago. It was at the old building, so it's been 6 or 7 years ago. I had, you know how I always complain about staples with tests sometimes? They get stuck together. Kid took a test twice. Didn't even realize that he took the test twice. He was so focused on taking the test. It's one of those like wrote their name on every page, so he didn't think about it. Or his name didn't look at number one again. He did worse the second time around. But you think about it, you probably got to the point where he's like, oh my God, this is the longest test ever, you know? It's like 4 pages instead of 2 or something. Started probably running out of time, so we're going a lot faster. Didn't even dawn on him. I graded them both and kind of laughed. And I said, I'll give you the benefit of the doubt.
I would have noticed by then though that I'm doing the exact same problem twice.
But sometimes, some people you get such a mindset of just solve, go. You don't think about what's going on. It happens. So that was messy, but does that make sense how we sent through? What else you want to look at? What else we got? I know I told you guys I was going to walk you through a couple of these here.
Oh, can you do one of the ones you showed me in class?
Yeah, which one? Was it the one with the double root?
Yeah.
All right. 41 through 44 are all very, very similar in such a way that you have to do the same trick. I'll do one of them, and you can utilize the same trick for all of them, okay?
Do 44.
44, yes, do 44.
Okay. If I look at 44, oops, it's on the page. There's a couple of ways of setting this one up. Like I was telling Haley and I was telling second hour and stuff here, you have to get rid of the radicals, which means you probably wind up squaring both sides.
Twice.
Now, if I square both sides right now, I have to FOIL out with radicals. 2 radicals. I don't want to do that. I'm going to move one of them to the other side and just FOIL out with like 3 minus one of the radicals and turn it into a difference, not different squares, but a junk squared problem that way. It's easier to set it up that way. So what I'm going to do is go with the root 3 minus x is 3 minus root x plus 2. Okay. I don't think Bob Ross had the hair that poofy. I knew it was poofy, but it was more uniform of a poof. You got to throw the happy trees in there too, and draw him a friend.
Oh,
Okay.
I'm so confused.
Square both sides. What do you don't think I understand the Bob Ross reference there? Well, I know, but I know who Bob Ross is.
He's met him.
Square root of junk squared is always junk. Here I have to FOIL it out. First term squared minus 3 times junk minus 3 times junk gives you 6 times junk. And then I have subtract square root junk squared. Junk.
Yeah, I killed puppies.
Don't kill puppies. And also notice what I did with that last term. I threw it in parentheses because I have to subtract both pieces. Most people will forget when you square x plus 2, the quantity x plus 2, you're subtracting that whole bit. So do a rewrite. We have 3 minus x is 9 minus 6 root x plus 2 minus x minus 2. You okay with that? Oh, you know what? That should have been a plus. I'm sorry. I just realized that. I did minus, if I FOIL that out, this would have been 3 minus the junk. Negative junk times negative junk is positive junk. Sorry about that. So this would be plus x plus 2. So combine the stuff on the right, we're going to get an x plus 11 minus 6 root x plus 2. And I get that. How did I get 11?
Oh, I know, I got it.
So again, I'm still stuck with a radical on one side. But if I move some things around, I can have a radical on one side and integer and variables on the other. My suggestion, go with positive variables and positive radicals. Move the -6 root junk to the left. Move the 3 minus x to the right. By doing that, you'll get positive coefficients. Okay? I'm going to get positive coefficients by doing this. It'll be a little bit cleaner in the end. So now I have 6 root x plus 2, 2x plus 8. Now square both sides again. I had someone second hour actually divided by 6 and then squared it. Oh, you don't need to work with fractions here, guys. It's not a big deal. Sir?
You can divide by 2 though.
You could, but it's still, you still have to square with the coefficient. It'll wash out at the end. Okay, it does wash through, so it's not so bad. But you're right, you can divide out by 2. If I square everything where it sits now, I get 36 times jump. And then I FOIL out the other side. 4x squared. 2 times 8 is 16. Double it. And a 64. Move this up here. It happens. So subtract the 36x, subtract the 72. Now take out your 4. When I'm factoring this to find zeros, when I take out a GCF of a constant, does it have any bearing upon the problem anymore? What times what's -2? You add together to get -1. Which gives you possible zeros at x equals 2 or x equals -1. Which means way back at the very beginning of the problem, when we checked them, I think I did this one second. Did they both work? I think those both work. The idea here, guys, is that sometimes you have to do quite a bit of work to go through these. Okay?
Are you collecting this?
I did, yeah.
You should do 56.
Yeah, I'm going to actually do 56 and 58. Is 56 the one with the fourth and the half?
Yeah.
I didn't know.
Okay. I can't see it this way.
I got 56 and 57 wrong.
No, 56 is both halves. Which one is the one that had the fourth and the half?
And 58.
So I just wrote no solution.
Yeah, I wrote a solution like all the.
Like
No.
the thing after 4.5, that was on 40.
Oh, it's 40.
Yeah. I just want to talk about that one real quick.
How do you do 58?
I'll get to it. It's a lot easier than you think.
56, 57, and 58, I got fractions.
So, real fast, I wanted to show you guys this one on what you would do on number 40. On number 40, since you have 2 nth roots equaling 0, move 1 to the other side so you'd have root equal root, and then just raise it to the power that gets rid of the roots. What's going to get rid of a fourth and a half? What would I multiply it by to get rid of a fourth and a half? A fourth power. So what happens then is you wind up by moving this to the other side, you're going to get 28 minus 2x on one side. The other side would be x minus 2 quantity squared. you're eliminating the nth roots, or I'm sorry, the fractional exponents by multiplying by whatever the, I don't know, common denominator would eliminate both of them by getting rid of the fraction. Does that make sense?
Yep.
Just using power rules there. Now if I go back to 56, 56 is basically the exact same thing of what we just did, but they wrote it as a fraction exponent as opposed to a nth root. If it's easier to see what's going on with an nth root, I would do it that way. Everybody agree that that's the square root of x minus the square root of junk is 2? I'm just going to rewrite it as the square root of x is 2 plus the square root of x minus 5, and then I'm going to square both sides and do the exact same thing I just did. I will have to square it twice to get the solution. Does that make sense? Like I said before, there are times that when you're solving equations, sometimes it's easier to solve them with nth roots, and sometimes it's easier to solve them with square roots. A lot of the ones that we're done where it's just, if you have one root, it doesn't matter. When you have two roots, sometimes it's going to be easier to put it in, or exponents, sometimes it's a lot easier to see what's going on if you go to the nth roots. Yeah.
Why couldn't we just do what we did with the last one and multiply it by 2? Like, I mean, by 2. But the last time we just like, then we multiply it by like 4 and get rid of it. But we make it, so.
In this case, you can't just distribute over a binomial. You'd have to FOIL it out. If it was a monomial, like the other one was,
Yeah.
that's why that worked, because I moved it to the other side. And that's how I was able to get rid of the exponents, because there was just fractional exponent equal fractional exponent. There was no other junk in between. Here, when I move stuff around, I'm going to have 2 plus a root.
Yeah.
I can't do it then, because it no longer becomes junk squared or junk to the root. Okay, you got 2 terms. All right, that's how that one works. It's now from there you do the same thing we just did. Now if I look at 58, 58's a tricky sucker. Because it tells you that you're looking for, it has something to the 2/3 power equals something else. In this case, you sort up over by my carrots there, by the yellow papers and stuff. In this case, if I write it, that's perfect. If you write it up to get rid of that fractional exponent, I'd have to raise it to the reciprocal property of 3/2. Correct?
Yes.
Then how in the world do I raise x minus 7 to the 3/2? How do I write that? Can't. So you have to do something different.
You just don't do it.
No.
I just wrote
Just put a 0.
If I raise that to the 3rd power, using your power rules, what's 2/3 to the 3rd? Squared.
I'm confused.
So what I do to one side, I did to the other. I'm using power rules. If I rate 2/3 to the 3rd power, means you multiply your exponents together. What's 2/3 times 3?
Why is that?
Because I raised it both. What numbers are jealous? If one of your sisters got a new car, wouldn't you be jealous?
Well, she can't drive.
Yeah.
Why are you spoiling my analogies?
Because
Why were you talking about
Get out of here.
Now you have to FOIL everything out. Now here, remember, it's x squared minus 14x plus 49 times an x minus 7. So you have to go out with that one then. Uh, 14/7 is 98.
oh, that's pretty.
It is, isn't it? Something. 7 times 49, I believe, is 343. Pretty sure on that one. 7 and 49.
I thought you said 7 and 9. For a second, I'm like,
Now I move everything over to one side, and this is where it gets interesting. As if it's not already. So now we have x cubed minus 14, or minus 21x squared plus 147x. Move all this over here.
Oh, I wish I could do that.
It's nice, isn't it? Yo!
Why would it be 147x?
I had missed an x, I thought. This was supposed to have an x in it, wasn't it? Yeah. That's why. I forgot to put the x there. I did this problem earlier and I knew it was a 147. I just forgot to put down the x. So I have, if I move this around, then I have 0 equals x cubed minus a 22x squared, a 153x, and a minus 352. Wouldn't it be great if you could factor this one by grouping?
Yeah.
Maybe.
Too bad you can't.
You can't, because if you look at it, the first one has a GCF of x squared. The second one, I'd have to make it look like a 22. If I take 352 divided by 22, I'm pretty sure it's not going to work out to be for the other side. So you have to think about, well,
It's 16.
still doesn't work.
really?
You have to use synthetic. But you have to worry about the tails. This is where knowing what the problem's asking you to do and what technology you're allowed to use with the problem. I could throw this equation into my table and I could search real quick to see if I can find a 0. So I forgot the equation right. We have x cubed minus 22x squared.
How come when you put x in the calculator, it actually gives you like a real number?
What's that?
Like if you put like on the regular part and you put like x, it like gives you a real like decimal. Like they just put it in the really weird.
I'm not sure. I gotta look at that. You get a 0 at 11. Guys. You get a 0 at 11. Which means at this point, you use synthetic to break it down to a quadratic. I know it has to equal 0 because this told me so. So I have a 0. Guys, I have a 0 that I found using my table at 11. I know that. The other one is x squared minus 11x plus 142. Yeah.
Something I don't feel like.
So this is when you quickly look at this. The opposite of b plus or minus the square root. B squared minus 4 times a times c. Just by looking at the discriminant there, will you have a positive value? Yes, sir.
A p squared of 11 times 11 does that equal negative 11?
No, you won't.
Oh, did I write that? Sorry, it's 120. Anyway, I know that it wasn't going to work. It's 121. So this is what, 32?
That's right.
So it's still,
142 is so higher.
if I double 32, I get 64. I double that, I get 128. 121 minus 128 is a negative number. Can I have a 0? Can I take a root of a negative?
Negative.
So that means, this means that then,
You get I.
guys, I really, come on. I got a couple more I want to try and get through here, and I got a couple minutes of notes to give you. Again, going through all of this one does take time. You get to the point here where you're done because your last two remaining roots are imaginary, which means the only solution that you could possibly have is 11. We're not worried about imaginary roots here. So you just go back and check, did 11 work? Did 11 in fact work?
Yes.
And that's how you set them up. Okay? Yes, sir. Here's the problem. It depends on what's asked. Depends on the answer. What's the question asked? Is it just find 0? It depends, do I let you use a calculator to get this far? Could I write a problem in such a manner of this where you can get to a synthetic division portion and not have to worry about finding your first 0 at 11? Yeah. So there's a bunch of ways of going about it because there is calculator, non-calculator versions of this type of things. When it comes to a final, do I expect you to do all this work?
No.
Oh, heck no. You put the numbers of x in your calculator and you figure out which one works. Right. Or you set them equal to each other in your calculator and you look for the intersection. And you're done. It takes 2 seconds. Yes, ma'am.
Are we gonna have like stuff assigned to us like for over break time?
I haven't gotten that far yet. I still got a week.
Yeah.
Yeah, make sure your names are on that, send that up. I want to show you a little bit about what's called function notation, like I did with the second hour. A little bit of this with you guys like I did with second hour. We'll get into the rest of it tomorrow. I know we still have a shortened out tomorrow, but we'll be able to knock out the rest of it without too much of a hassle. Function operations is really nothing more than this. You will be given a couple of functions. You will be given two things like this, an f of x equation and a g of x equation. If you recall from back in Algebra 1, you guys were defined functions is that for every value of x, there exists exactly one value of y. So if you graph these, you would use that vertical line test to make sure that you did not touch 2 points at the same time. That's what that meant. Okay? It was a one-to-one and onto representation. You'll worry about that later on. So what's going to happen here is this. You're going to take these, it'll be asking you to take these types of functions that are given to you and create a new function, h of x, by doing the following. The f of x equation plus the g of x equation. It'll tell you what to do. This h of x can be created by any sort of operation. What that means then is quite literally direct substitution and combine like terms. What is your f of x equation? What's your g of x? What's 2x plus x plus 3? So your new equation, your new function is 3x plus 3. If it asks you to subtract them,
Where is this element what I actually understand?
we'll get there. This is just starting with where it goes. When you talk about functions, you think about a coupon. You have two things of a coupon. You have a $5 coupon and a 10% off. You have $5 off your price and then a 10% off coupon. Which one should be applied first to get your most money? That's where this comes from. Okay. You can do the exact same thing with subtraction. Oops. If I say h of x is f of x minus g of x. Again, it is quite literally write things down and combine like terms. One thing that you will screw up though, distribute the negative. It's such a common problem with this type of setups. Take your 2x and you're subtracting. Since that g of x function has two parts to it, sometimes it might have three. It might be a quadratic. It could be an nth root. It could be something. It could be anything. Right now, I'm just starting out real simple with linear stuff. Okay, we build into this later. you get 2x minus 3, or minus x minus 3, which is x minus 3. Okay. What happens if you want to multiply? You just distribute, right? What happens if you want to divide them? Divide them, if you can or you cannot. Sometimes you might have a common denominator, be able to factor something out and so on. Yes, ma'am?
Will we have to determine like which one we're doing, or is it just like, well, it's
It
hard,
is quite literally, you'll be given two functions and
it'll say-
operations to talk about.
Okay.
What's going to be a little bit different from what I'm showing you guys here today is that they will say, what is f plus g of x? What this means is, what is f of x plus g of x? That's all that means. They just write it a little bit differently sometimes. Yes, ma'am? We're going to talk about domains and ranges tomorrow.
So don't do that.
Don't do that part, no. Yeah, we'll get into, because I didn't want to get too crazy involved into it. I just wanted to get you guys familiarized with basically direct substitution and combined like terms, because it's not that crazy to start with. And then tomorrow we'll take those 6 problems and build from domain and ranges, and then start to figure out, okay, how do we create composites of them? And then how can you create inverses of them? And what are their domains and ranges versus the original domains and ranges? Stuff like that, how things flip-flop. It's building blocks. Yes, ma'am?
So you don't want us to do the homework?
I want you to do the homework,
Just not the domain.
just not the domain and range part, okay?
That's all the function of.
Yeah, so as you guys have already read across, on, I think it's what, 405?
Yeah.
Okay. On 402 is what I asked you guys to do, because I'm at the point here where I don't want to go too much further. I mean, I could do another one, but I don't think you really need me to show you how to distribute 2x to x plus 3, I hope. So what happens here is that I'm going to ask that you guys do these 6 function operations. And remember, if it says f plus g times x, that just means f of x plus g. If it says f times g of x, it means f of x times g of x. That's all it is. Okay? Yeah.
I forgot to put my name on this.
Well, so what was the triangle?
So we will worry about domains and stuff like that tomorrow. Not had a chance to talk about where that comes from and why that is and what we need to look at. We'll start with domains and how we use this stuff out of here tomorrow. We will also talk about the difference of f times g of x and f of g of x. There's a difference between that. It's kind of foggy.
So will we ever have like work problems, like
Oh
the
my
key
God.
point that you just talked
Yeah.
about? Okay.
And that's where it comes from. That's the idea of why do you have composite. Functions are, you can take any formula, I mean, you think about a 10% of coupon. If it's something's 10% off, you just multiply it by 0.9. That tells you the new price. If something is $5 off, you take that value, subtract 5. Well, is it going to be cheaper if you take 10% off the total price first and then subtract $5, or is it cheaper to take the $5 off and then subtract 10%?
Depends on the price.
And then depends upon the price, and that's where things come in. How do you create those composite functions to be able to do that? That's where this stuff comes into play. Okay, you're right. It's not an everyday scenario, but it does come through here quite often. And like I said, this style of nomenclature, this style of writing problems out, is hugely popular on standardized tests. Okay. Hoppenworth, you're about to say something. You look perplexed.
I was just thinking about for like 25 and 26.
Yeah.
What do you mean by like something?
Okay. This means take 2x squared plus x minus 3 and divide it by x minus 1. And you know a bunch of different ways to do that. Do you? I hope. I can think about 3 different ways. That's one way. Long division's another way. And synthetic division's the third way. Yes, Lalan? Yeah, those 6 for tonight, yeah. It's those 6 for tonight. It's on the calendar. Whoop. What do you want?
So like the first problem there, so like if I was to take f, so f represents 2x squared plus x.
Yes. Last time I checked.
Okay, alright, I got it.
Another thing that will show up from time to time is this, and we'll get to this more tomorrow. What is f of g of 3? All that means is, what's the innermost parenthesis? What's the next letter? Take 3, substitute into g, get an answer. Take that answer and substitute in f, get an answer. It's a composite function.
These are so easy. Just these are extremely hard.
They not only will write these out in terms of f and g's and things like that, they'll write them out in terms of triangles. Triangle of x is blah, triangle of x is something else, and so on. It's quite interesting. You were here.
Mr.
Yes, sir.
I have a question.